try that link. That looks actually like what you want. Although, as you say, it's an HTML tree of a bunch of stuff.
Yeah, yeah, I think that's the one.
Part of.
Yeah,
you get each of the programs in plain text.
And I'm finding one on the mx.cs.hm.edu.
Yeah.
That seems to have sort of related information, but not the actual text.
I believe it has the actual text of the programs. Look in the chat for the meet that we're in. If you open up the chat, I've pasted a URL on that website where you're on. But like if you click down, just following the first couple of links, you get to algorithms that look like this. This is the Easter Sunday algorithm.
Right. So that has like, well, that has the programs, but not the the text of it.
Oh, I wonder how much more is the actual text.
Yeah, there isn't a lot of text. There is, it is, it's useful. So there's text where, within the text, if there's references to mix, so then there's this alternative newer version of that. But I think the more important part is really the programs. So the other texts, you can sort of interpolate looking at the original.
Okay.
But yeah, I would still recommend if you can get a copy, that's the best, because I'll have references for the page numbers for the copy, and then the copy does have the page number references to volume 1 or to TAOCP, so it makes it a little easier to link those two things together.
Okay.
We'll just wait another maybe a minute or two if somebody else is going to join. But this is the agenda for today. So not a lot of material, but since it is sort of our initial foray back into the main text, I thought we'd go a little slower. The initial material is, again, sort of this general introduction to these very basic data structures, linear lists, and it doesn't really get very technical, so I think we can read a few pages at a time, and then hopefully we'll have some time after the break to do some exercises as well. And by the way, as far as exercises go, if anyone has, like an exercise or something from a previous meeting, any of the previous meetings, so feel free to bring them up, bring those topics up after the break, and we can definitely go back to revisit some of the material. So if you're joining the meetup for the first time, we'd appreciate if you could just say where you're connecting from geographically. Most of us are in the New York region, New York, New Jersey, that area. But it would be nice to know where you're connecting from.
Is Avtaj, I'm audible?
Hi, Arvind.
I'm from Mumbai, India.
Oh, you're connecting from India. Okay. So
Yeah.
what time is it there?
12:45.
12:45. Okay. Well, that's pretty amazing. Thank you so much for joining.
So, thank you for doing this online.
All right. Cool. How's the connection? You feeling? I mean, we're hearing your voice pretty well. There is a bit of background static. I'm not sure if that's the connection, but you seem to be coming in, pretty clear. How are we sounding to you?
absolutely clear.
Okay.
That could be the fan behind me.
Yeah, it sounds more like a fan or road noise or something more than
Yeah,
a connection.
that's great. Okay, so just a quick review of our process. It's pretty straightforward. We're trying to read through the art of computer programming and study and do some work related to it. So we have, like a bunch of pages that are sort of the subject or the agenda of each meetup. We read a few pages at a time. Generally, we'll try to keep the reading to about 5 to 7 minutes, and then we'll discuss things. Hopefully people will have some comments on what they read, or they'll have questions. And that's really the point of this meetup, like just giving everybody an opportunity to read something, reflect on it, and clarify it, and then work through some exercises afterwards. Um, we do go over, other related stuff from time to time, and everything that we do, I try to make it available relatively soon in the form of videos and chat copies in our GitHub repo, and there's some work as well there on exercises and programs. So today, as I mentioned, where we finished in the sense that we went through the MMIX introduction, and so even if everyone has not really worked through everything related to MMIX, the videos are there. There's some of our discussions, some of our work as well. So hopefully that will serve as a good resource. And then as we come across the need to understand more about MMIX, then some of us have a better understanding than before, and we should be able to help anyone. So I don't think there's any particular concern, or there should be any concern, like how am I going to keep up or not. So don't worry about that. So today we're going to start on volume 1. This is going to be the main TAOCP Chapter 2 Information Structures. But as I mentioned, and as has been mentioned in the notes for the meetups, that the computer that we're going to be using is the newer version of Knut's design, which is called the MMIX. And all the current printings have the programs and the code in the older MMIX with a single M computer. And so we have to use this MMIX supplement, which has MMIX equivalents of the code and other pieces of the text that in the original are still referencing the old computer. So I just wanted to give everybody a chance to look at the MMIX supplement, how it's laid out and what it's covered. So we'll just do that for a few minutes and then discuss that, and then we'll dive into TAOCP. So we are now going to open up the MMIX supplement and basically just skim through pages 7 through 29. So there's a foreword, there's a preface, there's a style guide, which is quite useful. You'll need to come back to that again and again. It has important stuff related to MMIX. There's a table of contents, so till about 220 or so, and then we'll discuss. All right. Any comments?
Well, I'll say I only probably halfway through. I'm looking at the style guide still.
Okay. Yeah, if you
Fine,
want a
fine,
couple
get
more
more.
minutes, we can do that. But my goal was really, there's a lot of stuff in there. And again, I think we will be coming back to the style guide and the programming techniques quite often to clarify things. Just wanted to let you know where things are, where to look for things. But yeah, Arthur,
I'm not
you
saying
can. Did you want to spend more time on it, or we can move on?
Not particularly. I'm not suggesting we spend more time on it, just letting you know that if you're asking what did I think of the second half, the answer is I didn't get there yet.
Yeah. So you asked an interesting question about the .s suffix for assembly language files and source files. Yeah, I don't have an answer to that. Does anyone know, or anyone can look it up? Maybe Wikipedia? Was there a Wikipedia reference for assembly language, history of assembly language source?
Yeah, I've never seen S used as an extension for assembly files. I have seen O for object files, so maybe it's kind of paired with that.
S is very common on like Linux and POSIX type operating systems. I'm not sure about Windows.
Yeah, I do agree with that. S is pretty standard actually, and also the option for generating the assemblies is also S, I think, -S.
Yep.
Yeah, there must be a very good reason for that. It's true.
I mean, it might stand for source. I guess I already said that. But anyway, I don't know. I'm gonna ask later. Give me some internet points.
Okay.
When you say the option, you mean like you do a compile from C to executable. You say also give me the source or the assembly source. It's -S.
Like if you're compiling to an object file, you'd say -C for compile. If you're compiling to assembly, you typically say -S.
Okay.
It gives you the assembly output.
Yeah, if you wanted to generate the assembly and have a look at the instructions.
For a C or C++ compiler.
Does it stop there, or does it go to the the object also?
No, for the object, you would say -C if you had a .o file.
Okay.
Okay.
But anyway.
Yeah. Any comments on Knuth's introduction? I think that's the foreword that he wrote.
I was pleased to see that it starts out with the idea that the important thing is to be able to move effortlessly between different levels of abstraction, which is something that I complained a little bit about a week or two ago, that he does this a lot implicitly in the book. And I think that for people who maybe aren't good at that instant switching between, oh yeah, he multiplies by 8 because it's bytes and then here it's bits, that's just a special case of this general idea of we're thinking about things in two ways simultaneously, right? An algorithm and the instructions that make it up, and like what is the computer actually doing when it runs this thing. This is all mashed together, and you have to keep it all in your mind together.
Yeah, and I think that as you program more and more and you gain more experience, I think that's needed at many other levels as well, right? You're switching between, let's say, a system design, and then at each component level, and then how each one of those things are implemented, and it's happening at many levels of abstractions. If you're working in some object-oriented language, then class design, and then sort of the individual data fields, the function fields, and things like that. But yeah. pretty interesting. Okay, so let's move on to now TAOCP itself. And we're in chapter 2, information structures. We are reading the introduction section, pages 232 to 236. And there is a little bit of content here for which there is an equivalent replacement in the MMIX supplement. So I've given those page references there. So if you get a chance, have a look at that as well. And James has a comment in the chat if anyone wants to read it about the -S.
Also, in the text, I'm using the second edition, so my page numbers are a bit different. We're going right up to the exercises.
Yes, it is the entire introduction section. Yes.
Okay.
Yeah, I'm really sorry about that, that I'm not able to give you the references exactly for the second edition, and I'm sure that the text snippets are also a little
Right,
different.
yeah.
So
I remember last time, like being like paragraphs, like missing. Right.
So till about 232 or so. Okay. Arthur has pointed out that in the paper copy, these are pages 15 to 16 of the MMIX supplement that I've called 49 to 51. Yeah, I was referring to the PDF in this case. But yeah, thanks for that. So this is quite a bit of material, but he's sort of laying out the introduction to how programmatically we will, refer to certain simple linear structures and parts of those structures. So any questions?
Well, actually, the one thing it reminded me of, I used to be a member of the C++ standardization committee. And at one point in the standard, it had to define an array. And the array, one of the critical details of an array is that it's in contiguous memory, which leaves the question, what exactly is contiguous memory? And it's like, well, the bytes are next to each other. It's like, well, what exactly does next to each other mean? Are the diodes next to each other? And so, like, the addresses are sequential, but with a paged memory, they don't have to be sequential. And it was like, a rather long discussion about how they could, specify that in the standard.
Yeah, so over here, it is a little confusing at first, I think, that he keeps calling them lists. He actually doesn't use the word array so far, I think. So he's sort of left that at some abstraction of these, things that are next to each other, laid out linearly, whether they're, in.
Well, but these things aren't laid out linearly. Here,
I'm sorry?
when he says capital L list, I mean he's thinking in terms of list, but the data structure he's describing is a linked list. If you look at the addresses on page whatever it is, but somewhere in here he's got the. Wait, is that only in the supplement? There was no. Okay, here it is. The in this little diagram here, these memory addresses are not in numerical order. He's written them sneakily there, but the list itself starts at memory location 242, and then the next node is at 86, and the next one is at 100, and then there's a null pointer,
Right.
which is called
what I'm saying is that he's not talking about how these things are actually present in memory, like they could be in contiguous memory, in the form of a contiguous region of memory. But yeah, the individual nodes are linked to other nodes using some next field.
Right.
I'm thinking whether we should maybe do one of the exercises right now. How does everyone feel about that? From the MMIX supplement, if you look at exercise 1, so this is
Wait, from the
at the end of that section 2.1 in the supplement.
My paper copy only has 7, 8, and 9, I think.
I'm sorry. Yeah, the actual exercise number is 7. You're right. It's the first exercise in the supplement, but the exercise number is 7.
All right, sure. This looks relevant to our interests.
Yeah, I think it'll clarify some of the things in the algorithm as well, the 2 algorithms that were mentioned.
Or at least remind us all that we don't know what any of these sequences of characters mean, and we have to go look it up again.
So LDA is load address, which is taking the address that's associated with the variable top, loading it into a register that is named T, so that's some register. And then LDB is load byte, so it's taking 1 byte of memory, and it's, well, first of all, it's taking the address from T. If you look at LDB, it's got 3 operands, right? So the first operand is going to be the destination, which is a temporary register. But the second operand, which is T, which right now holds the address of top, and it's going to add suit to that address in T, and it's going to that address and get a byte from there and load it into T.
So, so Knuth's notation, suit parens top close parens, that means the suit field of the variable of the card pointed to by top. Where
Yes.
top is a pointer, right?
Yes.
Or what he's calling a link variable is a pointer variable.
Right. Right. So yeah, but in the assembly itself, because there's no parentheses like that of, you know, sort of referencing or dereferencing. So suit is just that address, or that offset, sorry.
Right. So I claim that A and B do the same wrong thing, and C does the right thing.
Okay, anyone else? Arthur says C is right, A and B are wrong.
And more than that, I think A and B do the same thing. I'm not 100% sure about either of these.
Okay, yeah, we can go over that, but in terms of being the right sequence, does anyone else have a different choice than C?
I want to hear from some of our silent people.
Yeah, I don't have the supplement, so I can't.
Oh, weren't you able to, this, yeah, I don't know if this is on the website either.
On the website, it has the answer, but doesn't have the question.
It has the answer, okay.
On Amazon, it had the peek inside, that only had the foreword and the preface. In the first chapter, didn't get up to the second chapter, which is what we're on.
Okay, so I kind of explained A, best I could. Could somebody else explain B and C? Not Arthur, because he's already figured it out. Somebody want to give B a shot from what you remember or what you think it might be?
Just put the options in the chat for James.
And what are our goal of these options?
What's that?
What's the goal?
The goal is to bring the quantity top of suit into T. Or, sorry, suit of top.
So one of the things that you'll notice is that in C, the first instruction is a load octa unsigned, which is going to take the address which is associated with top, and then it'll load that octa value in T. And then LDB, which is going to load a byte by adding the suit offset to that octa that we've loaded, go to that address and get a byte out. And the other two don't have the unsigned. suffix. Okay, well, Arthur, do you want to explain why you think C is right and A and B are wrong?
Okay. So, well, I started by looking at B, which was the most clearly wrong of any of them. That says take top and add suit to it.
Mm-hmm.
And we know from the style guide that whenever we see something in capital letters like top or suit, that's going to be some small integer, I think. Or anyway, something that felt like here we're adding two numbers, not adding an address. And well, we are adding an address. Anyway, this felt wrong. So top here, when he says it's a link variable, he means that top names a place in memory where if we looked at that place in memory, we would find a pointer. And so the operations that we want to do is we want to go there and get that pointer, and then we want to go there plus suit and load that byte. So taking the address of the pointer, which is top, and offsetting it by suit would be correct if there were an actual card at top, but there isn't a card at top. There's a pointer to a card. So given that there's a pointer to a card at top, we want to actually go there and load the octa from that location. Now we have a pointer to a card in register in T, and so we want to then go look at that card and specifically look at its suit and load that byte. And so that's the sequence of operations that C is doing. First load an octa, so now we have a pointer, and then load the byte. A, I believe, ends up doing the same thing as B. Both of those end up basically just putting top plus suit in a register and then dereferencing it. So A and B would both be correct if top were the address of a card, but since it's the address of a pointer to a card, we want to use C instead.
Yeah, that sounds right. And I think over here, again, there's some conventions that they're using, and then there's just the assembly language instructions that you sort of have to become familiar with. But those are the things that we will need to really understand when we're looking at the code and then how that's being used to implement certain algorithms. Any other comments or questions?
I wonder if it's possible to do exercise 8 also.
If it's possible to do what?
Exercise 8.
Oh, sure. You want to explain what it's asking for?
So we've got this sort of algorithm B back in the main book, asking to count the number of cards currently in the pile. So starting from top, follow the next links in the list of cards, counting up in some variable n how many cards are in the pile. And it's saying write an MMIX program that does that. So this is sort of the inverse of exercise 7, where exercise 7 says, figure out this code in English, and this is saying, turn this English into code.
Yeah.
So after the exercise 8 is in the main book or the supplement?
And two supplements. If I look at that exercise, it's the same thing. Like 8 is saying, write a mixed program, and then supplements is elements. That's it.
Can you share the page number?
In a third edition, page 237.
Okay, thanks.
Okay, who wants to give it a shot? We can just go through like each step, like B1. So for B1, we've got two initializations going on. There's an integer variable n, and there's a link variable x. And n needs to become 0, and x needs to hold the value of top, which is an address.
Okay, I think I've got something, theoretically, except I don't remember one of the mnemonics. Oh, James is typing.
Go ahead, James.
I of course have not gone through the full. No.
That's fine.
Yeah.
Yeah,
So
it doesn't have to be exact as long as we get the meaning. LD1. So you basically want to load a 0 or set register 1 to 0. Was that the intent?
Yes.
Okay. So assuming that we're using the name n for register 1, then we can just say, yeah, Arthur has typed it out. So there's a whole bunch of set and increment, set, set, and inc variants that you can use to just set a register to a particular value. LD is going to mean that you're going to get something from memory and put it into a register. So, which you don't need to do with 0, for example.
Yeah, I haven't gone through the MMIX. I'm still looking at the mix. So.
Oh, okay. Then you'll have to educate us on what mix means, because I really did not cover that at all or read it. Okay,
right,
so we've set n to 0 using like a set instruction, and then what we want to do is to load top, or actually we want to get the value that's stored at the address associated with top and get that into a register.
Okay.
So that would be don't you want the same thing as in exercise 7? The LDOU? So we're going to start with top, and so essentially we have to do the same thing as in choice C. Okay, so now we have in register T, except in the algorithm he calls it X. So, well, does he call that X, or X is referring to the, yeah, I guess X is not a register name. Yeah, so we still need another register name. So we'll use T for the temporary register. And then what about B2, which is going to check if this link variable X is lambda. What is lambda supposed to be? Like, what is the value of lambda supposed to be? Is it 0?
He's a little coy about that, but says, yeah, it's usually 0. 0 is convenient. But yeah, I think we're intended to assume it's 0.
Okay. Yeah, I don't remember reading that explicitly. I thought maybe I missed it, but yeah, all right. So we'll use 0. So how do we do that comparison? How do we check for that equality? So there's the comparison instruction, CMP, is it CMP or CMPU?
So I just put in chat what I came up with. I'm not sure how this matches up to what you're building too, though. In particular, I ended up not using the CMP.
Okay. So jump to step 2. And in step 2, you're doing a branch non-zero. If X is non-zero, then we branch. And okay, so you're right. You're using the fact that we're using 0 for lambda, and so if the value that we loaded from top into register X is 0, then we've got lambda there. And if we have lambda there, then what should happen?
Then we don't branch, and then we fall out the bottom, and then N still has 0.
Okay.
And had no elements, and so we're done.
And if we do branch and we go to step 3, we're going to add N and 1, for which you could also use the increment instruction.
Oh, there's a separate increment? This isn't risk at all. I didn't actually remember that. Okay.
Either one is fine. And then we go on to the next instruction, which is meant to assign the next field of X to X.
There is no increment instruction. I was right. It wouldn't make any sense to have one because every instruction is the same size, right? It wouldn't. What would it save you?
I thought that there are increment instructions.
There are on real platforms, or at least this platforms like x86. But there it's because an add is like, I don't know, 5 bytes and an inc can be 1 byte. But on RISC, where everything's the same size anyway, I don't think it really buys you anything. If the hardware decided...
No, we have 4 increment instructions. Increase by high wide, increase by medium high, increase by medium low, and increase low.
That's not what we want to do, but I wonder what it would...
Increase by, if we use increase by low wide.
Right. Now I'm trying to find where those are.
Increase by low wide should...
oh yeah, okay.
Right?
So you could also say inc L of N by 1.
Yeah.
That does do the same thing. That actually, in retrospect, surprises me that the addition actually does care, that the carry goes all the way through. I would have expected it to only modify the low wide at all, but I guess not.
Yeah, so those are pretty useful, you know, if you're working with some small numbers and you want to fiddle around with the register. But yeah. Okay, so yeah, this looks right. I was thinking, okay, we do the comparison and then we would do a branch based on that comparison. But yeah, you've just eliminated that comparison because we can just test that null value directly.
So the load sets the condition codes?
The condition code, yeah, go ahead.
The branch non-zero takes X as an argument.
Ah, okay.
Branch non-zero X.
So there's a comparison and a jump.
Yeah, implicit comparison to non-zero. Yeah.
Yeah, so I'm used to things where the jump just is based on what the condition codes are currently set to.
Yeah. Does Mix do it that way?
I don't know. I'm used to, like, you know, Z80 assembler.
Yeah, I know all real processors do, but
right.
But MMIX is magic.
And the Z80 is kind of crazy, where they a single byte register increment would set the condition codes, but a double byte 16-bit register increment would not set them.
Huh. Because they're using all their brain cells to do the 16-bit addition. They don't have any left over to set the flags?
Apparently not. But that you know, that was a chip from the 70s, so.
Okay, so that's pretty good. I hope that that sequence of instructions that Arthur's typed out in the chat, that's clear. But if it's not, please ask, because that's the goal of our meetup, is to really just spend this bit of time figuring these things out.
I'd say on the sort of the the MMIX Supplement website on that at the college, where they have the answers, they do have it very much the way Arthur presented it.
Okay.
Oh, with the add, not the increment, by the way.
Oh, okay.
No, the one difference though, they have P, B, and Z instead of B and P. I'm not quite sure what the difference is there.
Arthur can explain.
Oh, so the PB, so PBNZ, right?
Yeah.
Yeah. So last week we talked about this, right? This is branch prediction. In static branch prediction that the human has to be responsible for some reason. That MMIX has both branch if whatever and probably branch or probable branch if whatever. That means this is a backward branch, but I don't trust the computer to figure that out. I'm going to tell it. So yeah, MMIX is special.
Okay.
And by the way, for posterity / the quiet people, I didn't just like type out that code in order either. Like paper and pencil helped immensely, and I did not write it in order either. I started at the top, and when I got to the branch, you know, the jump to step 2, I went down a few lines and started with step 2, and then said, okay, now I go back up here, and it turned out I had the right number of lines. But yes, that was by no means written in order.
Okay, great. So we're just a little past 3. Let's take a 10-minute break, and when we come back, we'll continue with the next section on stacks and queues and decks.
Mm-hmm.
Okay, we're back. And whenever you join, if you can just start reading section 221, stacks, queues, and decks. This, I don't think, has any references to MMIX, so we won't need the MMIX supplement for this. It's just the main TAOCP. All right. Would someone summarize the section?
Well, I'll give it a shot.
Okay, thanks.
Or maybe I will. I've got some echo. So basically, we're introducing this idea of linear lists, distinct from what he called capital L lists in the previous reading, where there he was really talking about linked lists. And here he is talking more abstractly about just any ordered collection of data and the operations that you can do on it. In the very first, second paragraph, he says, we consider not only the data structure, but also the class of operations to be done on the data, which I think is an important takeaway of, the operations, the behaviors of the data are just as important as what it looks like in memory. And they're related, right? What it looks like in memory is going to affect what we can do with it. And so he's talking here about, well, what are the things we might want to do with it? Maybe put something on one end of the list, or put something on the other end, or take something off of either end, or random access into the middle. And if we ignore random access into the middle and just think about things that are restricted to modifying the ends, then we basically have three different kinds of data structures: the stack, the queue, and pretty much everything else he's lumping into deck well, we do stuff at both ends. That's pretty much it.
Okay, yeah, that sounds like a pretty good assessment. What did you think of the analogy with the rail tracks?
Yeah, works for me, except that that does turn your cars around, so that there's a little bit of leakage there in that metaphor.
Yeah, I always like using the plate dispenser at a diner.
Mm-hmm.
That's the one I've always been told.
Does he mention that? I seem to remember that
Yeah, it does. Very
mentioned
brief.
it somewhere.
He likes the train cars better, but he does on page 241 say an analogy with the stacks of plates often found in cafeterias.
Okay, there you go.
But then he does also say he doesn't like that because when you put a plate on and you push it down, you're shifting everything down. And in real life, that's not what happens. It's more like a stack of hay bales where you just throw another one on the top. The other ones don't move. Right?
Yeah,
So,
yeah, that's a really great point, actually. If you really want a similar behavior, then that is kind of different. Yeah, when I first read this and I saw that picture, I looked up how rail track switches work. So there's a whole bunch of videos on YouTube that are very informative, pretty interesting. So, okay, any other questions, clarifications that we may want to make or need to make between these three types of data structures? Otherwise, we can just go to the exercises. Okay, maybe that'll just help bring issues to the forefront. So let's just start with exercise 1. This is in TAOCP at the end of this section 221. It's the one that is rated 06. And I don't know if James, you probably don't have this. Let me paste this in the chat. If I can. So basically the question is, can you
Because
use, you got it? Okay.
that's in my book, yeah.
Oh, it is? That's great. Okay, so an output restricted deck would be you're allowed to input on both ends, I guess, but you're only allowed to output from one end.
Well, it seems like in the premise, they're talking about an input restricted one where we consistently output from one side. So it's physically a deck, but we're going to use it as as just a stack or a queue.
Mm-hmm.
Well,
So
in his terminology, an input restricted deck is a deck that you physically can't push onto one end.
right.
You can pop from either end and you can push onto one end.
But you're going to put a further restriction on yourself. You're only going to use one end to output.
Right.
Right.
And
so,
depending which end that is, you get either basically a stack or basically a queue. Yeah.
Right. So
the same is also true of the output restricted deck. You just pick one end to say we always push from this end, and if it's the end that you can also pop from, then you have a stack, and if it's the opposite end, you have a queue.
Yeah.
Okay, next one, James, it says in our version, imagine 4 railroad cars positioned on the input side of the track. So that's, do you have the same?
It appears to be. It appears so.
Okay, and then he's asking about these permutations. Okay. So we can spend a couple of minutes just reading that. I'll paste it anyway.
Okay.
And for those of us who are smart but lazy, exercise 3 is a big hint to exercise 2.
Yeah.
Now, I guess the first question to ask about that problem is the stack big enough to hold like all 6 cars at once? I mean, from the diagram, it seems not, but I'm peering now. You may have like a more virtual memory available.
Yeah, I mean, I'm sure for the purposes of the exercise, we're supposed to assume that it's big enough. Although that strikes me as an interesting generalization, and now I'm looking at the other exercises. Like, is he gonna generalize it to that?
Can't be done. I don't think we could do 3, then 1, then 2.
I concur.
So you're referring to the first permutation, the 3, 2, 5, 6, 4, 1? So there's two permutations being asked about.
Yeah. This is something like a general what would be impossible. Then we can work on if like those particular ones are possible or not.
So is there a restriction on how many cars can be there in the stack?
No, I think it's supposed to assume there is no restriction on the size of the stack. Certainly for the purposes of the exercise, there's not a restriction.
Yeah.
I think one higher number. Can't talk. I think one higher number cannot be followed by 2 lower numbers. 2 lower numbers are in increasing order. So 3 cannot be followed by 1, 2, because in order to get 3 in the output, you have to push 1 and then 2 on the stack, and then 2 comes out before 1. So they'll go into decreasing order in that case. Can you guys hear me?
Yeah, there's some noise, I think, from Arvind's end. Okay. Go ahead, Michael.
Oh, wait a second.
Michael, try again.
I was trying to come up with a rule for what you can and what you cannot do, and I'm thinking if there's a high number followed by 2 more lower numbers, like 3, 1, 2, the 2 lower numbers have to be in decreasing order. So if it's 3, and then any number of things in between, and then a 2, and then any number of things in between, and then a 1. Actually, there would never be anything in between in that case. But anyway, the numbers have to be. If the numbers are out of order after the bigger one, they have to be decreasing. And my logic is that as you're working on it, you come to a point where you want the 3 to be outputs. So if there's a smaller number than 3, you have to push that onto the stack. So your 1 and your 2 will go into the stack in reverse order. And that's the order they have to come out. So the 2 has to come before the 1 if it goes onto the stack. So the rule is big number followed by 2 lower numbers. The 2 lower numbers have to be decreasing.
That sounds approximately right to me. I'm not sure I've wrapped my head around it exactly, but
I don't know whether that's the only impossible thing, but that makes the second one impossible to do because you have a 3 followed by a 1 followed by a 2.
right. And it makes the second example in the exercise impossible because you have a 5 followed by a 2, 3.
Okay, so is the first one possible? 3, 2, 5, 6, 4, 1? How would that happen?
Well, we put 1 on, we put 2 on, we put 3 on, we take 3 off, we take 2 off. Then we put 4 on, we put 5 on and take it off, we put 6 on and take it off, we take off 4, we take off 1. So yes, the first one.
So the first one's possible, and it doesn't contain any how can you say high, low, middle numbers? The second one has a 3, 1, 2. I mean, you can take out anything in between. 3, 1, 2 is impossible, no matter what comes in between, because you have when you get to the 3, you're going to have put the 1 and the 2 on the stack. They're going to be in that order. In other words, 2 is going to be in front. And then when it comes time to take out the 1, you can't do it because you'll have to take out the 2 first.
Okay.
Okay, so I think, I missed the how to get a package, but seeing the basic rule is for any number on there, all lower numbers must be in descending order.
Well,
Okay.
Not quite. You got to look for 3 numbers that go high, low, medium in that order. If you have that sequence with any of the 3 numbers, then it won't work.
Right.
Because if you just have everything in reverse order, then just put everything onto the stack and take everything off, and it works. So if you had 6, 5, 4, 3, 2, 1, you put everything onto the stack, and then you take them off. Those are decreasing numbers, and that's fine.
Right. Well, but the way I'm generalizing it is for every number on there, every lower number has to be in descending order. So, the 154.
Yeah, that's it. I think you got it. I think you got what I'm saying. I think we're on the same page.
Right. Yeah. So like the 1's okay. So nothing's lower. For the 5, 4 is lower. 6 is not lower, so don't count it. 2 is lower. 3 is lower. 2 and 3 are not in descending order, so they fail.
Yeah. I think if you're trying to count the number that won't work, your condition is stronger and a little harder to count, maybe.
Right.
Because you're looking at all the numbers, and I'm just saying, just find 3.
Right. Yeah.
Okay, so Arthur's posted the theorem that basically is saying what you guys are saying.
Well, I think it's like my rule is what you have to do to prove if it's okay. So, like, if you know it fails, you just got to find 3. But if it works, you've got to prove it for
Right.
that it don't exist.
So that.
Oh yeah, that's exactly what I'm saying. If you put it in that language,
That was yeah, 3 exercises down. Exercise 5.
I didn't see the exercise. I just.
Yeah, we believe you. We believe you.
You came to that answer because that is apparently the right answer.
So 3 is also kind of related. Is number 4 also related? Yeah, it is. Actually, 4 is supposed to be a formula for what we tried to do in 2. How many permutations can you generate using a stack like that? Okay, so we saw 1 of whatever that number is. So what is that number then? Now, if we assume that we know 5, for example, can we do this quickly, or will it take a bit of time? Now, I'm asking about number 4.
I bet I can do it quickly with Google. So, as my previous comment indicated, and Knuth gets to this in exercise 3, he talks about representing these as strings, and he chooses S and X as the 2 characters in your alphabet. But if you choose open paren and close paren, it gets a lot more natural looking. And then the question is just how many strings are there containing 2 parens and 3 close parens such that they brace match correctly.
That's a common coding interview problem, kind of a test, where the way you do it is you go along and for the S's you add 1. You go from left to right, add 1 for the S's and subtract 1 for the X's. If you ever get negative, it's impossible.
Okay.
And
so what is that number there? What is that number for exercise 2? We had, well, 6 is a pretty big number. Let's do it for 4 maybe, or maybe even for 3. For n equals 3, what is the number?
Oh, that's a good way of counting it. Yeah. Because every SX, whatever it is, it's going to give a unique combination, and those are the only possible combinations that are going. Those are the only possible permutations that are going to work, right? SX.
And now you also have to show that each possible set of parentheses leads to a distinct permutation, which is also
they're all going to be distinct because.
Something it's in here. Yes, that's also exercise 3 is show that they're all distinct.
Well, because if they're different anywhere in the middle, then they're the same up to that point, and then at that point you're going to have an S on one side, which is going to put the thing on the stack, and you're going to put something else in the output, or you're going to put that thing in the output, and so whenever the S and the X are different, then the corresponding element is going to be in reverse order. Wait, the SX, S puts it onto the stack and X takes it off the stack. How does it get right from the input to the output?
Put it on and take it off immediately.
Oh, SX, right. So you do SX to put it into the, oh gosh, does that still work? I think it does. I'm thinking if you do SX, is that going to be the same thing as SX? But no, obviously not. SX is going to put the first input onto the first output. SX is going to put the first two elements from the input onto the output.
This seems to also be related to pancake sorting, right? But essentially, the only operation that we can do at all here is we have this this list of numbers coming in, and the only operation available to us is take some number of them and reverse their order, and then recursively we have some left over, and we can take as many as those as we want and reverse their order. And we can trivially just reverse one, which, you know, just moves it over to the output, or we can reverse two, or we can reverse three. But we can't do anything more complicated than that. And so basically, yes, so basically what we're doing here is taking the set of from 1 to n, and we're partitioning that string into as many partitions as we want and reversing each partition. We can reverse the whole thing by putting it all in the same partition. We can leave it exactly the same by chunking it up into partitions of size 1. But essentially, there are going to be as many possible outputs as there are partitions of n. And that, I suppose, must also be the Catalan numbers. I'm seeing a lot of Catalan numbers lately.
Is there a way of getting at the formula by eliminating the impossibilities?
I mean...
Well, you've got n factorial to begin with, like the total number of permutations.
Yeah. Well, we start with just, you know, 2 items, you know, 1 and 2. We can, now there's 4 possible ways of dealing with a stack. You can do, you know, sorry, I did that wrong. Just one thing. You know, you can push it on, take it off. That works. You can push twice. That fails. You can pop and then push. That fails. You can pop and then pop. That fails. So out of the 4 simplest operations, only 1 actually works.
Right, so yeah, go ahead, Arvin.
Yeah, what do you mean when you say fails, James?
What do you say? I didn't quite gather that.
I mean, you have 2 numbers, and you pop one in and you pop one out, and then the next one. But like in the previous examples, you pop both in and then pop them out in reverse. That's also valid, right?
Well, actually, I said that wrong when I said 2 numbers. I meant 2 operations. So, you know,
Okay.
2 operations.
When you have 2 cars on the track, then the string is going to have 2 S's and 2 X's. Otherwise, it's going to be invalid. It's not going to work. If you have too many S's, then you don't have any cars on the input. If you have too many X's, then your stack will underflows.
Right. So I was saying, if we just talk about 2 operations, you can do a push and then a pop.
If you have 2 operations, you only have 1 car. That's the only way to do it. That's what you were saying, I think. If you have
4 possibilities,
1 car, then you have 1 S and 1 X. Everything else doesn't work for something. And what I was saying is how many are going to work. And the way you can quickly tell is if you started with 6 boxcars, then you're going to have a string with 6 S's and 6 X's. Mm-hmm. Because you have to, because that's, you can only, the X's are going to put it into the output, and you're going to need to end up with 6 in the output, and the S's are the only things that'll take it from the input, and there's 6 things on the input, so you need 6 S's and 6 X's. Nothing else will work. And then you have the rule that if you count that string from left to right, and you get a -1, if you increment for the S and decrement for the X, then if you get a negative, then it's not a good string. You have to remove that. Somebody's confusing themselves. Arthur, you're never confused.
Well, every time I recount, I get an answer that's one bigger than I got last time. Initially, I said, well, let's just look at the friends strings. And it seemed like there were
You say
three.
that like it's a bad thing.
And then I counted again a different way and got 4. And then I went like, oh yeah, I forgot a couple of strings, and now I got 5. So the only one that's impossible here is 3, 1, 2, which jives with your rule.
Yeah.
So 3, 1, 2 corresponds to. Oh wait, no. Yes, we can't get 3, 1, 2. What's the one I didn't count here?
Well, I was thinking. Well, to get the possible operations, we think of an S is a 0 and an X is a 1. Then for so for 2 operations, you have 2 bits. You have 4 possibilities. For 4 operations, for 2 numbers, you have 4 bits or 16 possibilities. And as far as I can tell, there's only 2 that work. Push pop, or push pop pop.
I don't follow how you're getting these counts. Why did you say 16?
Right. So instead of S and X, think of 0 and 1. So if we're doing an even number of operations, we either have 2 operations or 4 operations or 6 operations. So that's comparable to either 2 bits or 4 bits or 6 bits. So imagine a 2-bit number. There are 4 possibilities there, of which only one of them actually works. 0, 1. If we have 2 operations, or 4 operations, that's 4 bits. So we have 16 total possibilities. And of those, I can only think of 2 that work, which is push pop, and push pop pop. So far it's going the square root of the square root, from number of possibilities to number of possibilities that work.
Yeah, I think I'm not following the need to look at the operations, because I was just thinking of permutations, just trying to figure out, okay, so either we could count the number of valid permutations somehow, like I think what Arthur is trying to do, or you can count the number of invalid permutations and then subtract them from the total number of permutations. And so I felt like counting the number of invalid permutations given exercise 5, right? It would be sort of like, okay, we just find how many of those invalid sequences can there be. So if you look at 3, the total number of permutations is 6. And so since we know there's, Arthur, you got 4 as the valid number of permutations with 3?
No, I think now we're up to 5.
Right.
Yes, we are definitely up to 5 because of Michael's rule, which is also exercise 5.
Okay. For 3 numbers,
it has to be for 3 numbers, right? So exercise 5 says 3. So if it's 3 to begin with, then the only invalid sequences would be what?
3, 1, 2.
3, 1, 2, right. So you have to take that out of, subtract that from 6. And you're left with 5.
So any of the other 5 you can do.
Yeah.
So you don't have 3, well.
So the same thing if you now try to extend that to 4. So with 4, the total number of permutations is 24. So if we leave 4, like we consider, okay, 4 is the leftmost number. Then we've got 3 slots left. And how many invalid permutations can we have in those 3 slots? It's 1, as we figured out. right? So then we try to do the same thing with 3, with 2, and then with 1. So is it 20 with n equals 4?
If the first number in your output is a 4, then I think the only way to do that is 4, 3, 2, 1. Anything else is not going to work.
The only way to do that is 4, 3, 2, 1. No, why not 4, 2, 3, 1?
4, 2, 3 is not going to be possible. You
Oh
have a
yeah,
big
2,
number
3 is not going to be possible. Okay.
Yeah.
Well, so the answer should be 14, but I get this from Googling.
Okay, so
Are the Catalan numbers?
4.
I have not found out why exactly.
Okay, so something to think about.
I do feel like there ought to be some, well, no, I guess I don't. In a lot of these problems, there's some clever way that you can recast it. Like I'm used to problems where it's like you're trying to count the number of bit strings with a certain property, and you're able to say, oh, well, if I treat every, if I look at the not this number, but this number XORed by itself shifted by 1, or if I think of the strings as being the partitions instead of the places between the partition or something like that, you can often like work out, oh yeah, there must be exactly 2 to the nth of these or whatever. But of course, in this case, we know the answer is not 2 to the nth for any n. It's the Catalan numbers. So I guess there's not going to be any easy trick to look at this problem in a different way. And I wish I could come up with an example off the top of my head of this. But I know I've seen this multiple times.
Arvind, did you have some comment or question? Because I noticed that you unmuted a couple of times, but maybe we didn't hear you.
Yeah, the second number in exercise 2, I'm still not clear why that doesn't work.
The second permutation of 154623.
Yes.
So do you think that you know a way that you can get that number? Or do you say, I can't get it, but I don't understand why not?
I don't get it, but I don't understand why not. Yes.
Okay. So to get the number 1 as the first digit, we basically have to put 1 onto the stack and take it off immediately, right? There's not really a choice about that. And then we need somewhere to put 2 and 3. We can't put either of them out yet because we're trying to get to 5. So we have to put 2 and 3 on the stack. And then we have to put 4 and 5 on the stack so that we can get 5 off, and then we can get 4 off. But now we're in trouble because we still have 2 and 3 on the stack in that order. So at some point we have to pop both 2 and 3, and we have to pop 3 before we can get to 2. So there's no way we're going to end up with 2, 3 at the end of our output. It would have to be 3, 2.
Okay, got it. Got it.
And so the relationship there between 5 and 2 and 3 is basically that's the pair on the triple IJ that is referenced in exercise 5.
Okay.
Thanks.
So we're close to 4 p.m. here in New York. next week, we'll just continue with the next section. And I think I only selected one section because there was quite a bit involved here. There's, I think, 2 or 3 algorithms in there in that section. And then that'll also leave us a bit of time for exercises. So, and maybe we'll also do some exercises from today's section if somebody finds any interesting ones to do. So yeah, by the way, I mentioned the MMIX visual debugger, how it only runs on Windows right now, and an interesting project would be to make it run on all platforms using the browser. And so I was able to actually get a WebAssembly build of the necessary components, and I was able to do like a rudimentary run in JavaScript. So that looks actually quite promising. Of course, you'd have to design this whole full-fledged front end, and all of that's very involved. But just having the basic thing running, it seems pretty doable right now.
Okay.
Okay. Well, thanks a lot for attending. See you folks next week.
Okay.
Bye-bye.
This thing.
Thanks. Bye.
Thank you, Zartush.
Welcome.
I never know how to close these things. Just X out.